Now we are moving on to the most exciting aspect of this lecture, I guess, that you have been waiting for. So this is supervised learning. Obviously, all of these things that we have been doing so far are supervised learning, but I just wanted to emphasize that the things that we are doing in this particular chapter are supervised learning. I'm also going to talk about continuous and binary both at the same time in this chapter. And then in the next chapter, there are some topics about the unsupervised learning. Okay, so again, we are using the exactly same data. We are using the depth, and we are also using the same formulas that we have defined before. One was for the length of stay, another was for the depth, right? The variables were exactly the same. So for the first machine learning method that I'm going to talk about is the penalized regression methods. And why we call them penalized? Because in a regression, usually the sum of squares look like this. So what does this mean? This is the observed y that you get. Say, for example, length of stay, original observations that you had. And this is the model. So this is basically the predicted value. Remember how we calculated the error mean sum square? So these are the predicted values. And so this is how we calculate the root mean square error. So other than the square term, there is nothing else. But as soon as we start penalizing it, like there are two penalization parameters there. So one is the beta j parameter, one is the lambda parameter that we are using. So this is the penalization so that in the ridge regression that none of the coefficients can be forced to zero. So we want all of the coefficients to stay in our model. This is opposite of the stepwise process that we have just seen. In the stepwise process, we try to drop variables, right? Ridge regression tries to keep all of the variables in your model, so that it is a guarantee that you do not delete any variables. Lasso is completely opposite. If a variable is weak, it will like slightly push so that it is zero, so that variable gets dropped from the model, right? And this is a very useful technique for addressing multi-collinearity issue. If two variables are sort of giving same information about our outcome, lasso would be a very effective method in deleting some of the variables that are not really giving you additional information on top of some of the variables that are already in the model, right? Okay. Elastic net is somewhere in the middle. So it's like a mix of both ridge regression and lasso. So it is not exactly ridge because we are not saving all of the variables, and it is not exactly lasso because like the variable list will be bigger than lasso, right? So this is like a less aggressive version of the lasso method, right? So these are all of these methods that we could use. The cross-validation, 5-fold cross-validation, those are the same. Nothing is changed. In here, what is changing is the GLM net. So instead of GLM, we are using the GLM net, and GLM net is the package that does all of these cross-validation. Sorry, all of these lasso and ridge and elastic net type of methods. So when you have alpha equal to 1, right? When you have this alpha variable equal to 1, then what happens is that it will, and alpha basically means in here, it is going to be the beta coefficient here. And what it will do is it will give you the estimate of a lasso when you have alpha equal to 1. And in here, you see since this is a continuous variable we are dealing with, R square is again not that great. But if you had ridge regression, the only thing you need to change in the equation before is alpha equal to 1. Sorry, 0. Previously it was 1, now it is 0. So it will give you the estimate of ridge regression. And then you would have R square not very different than before, right? Then we could do for the binary outcome, we could do the same, right? See, for the binary outcome for lasso, we are just setting alpha equal to 1, and exactly everything else is going to be the same. What does lasso do? It just reduces your number of covariates, right? And then you are getting your ROC values. And when you do the ridge regression, the only thing that needs changing is alpha 1 to 0, and then you will have your ROC value is 0.75. So you see, when we did our simple logistic regression and nothing else, our ROC value was 0.75. When we did lasso, ROC value is 0.75. When you did ridge, the ROC value is still 0.75. So there are certain variables in that model that are already giving you enough information that changing the functional form of the model is not really impacting your ROC observation that much. Right? And you can also try to do elastic net. In elastic net, what you are basically doing is you are basically like you can choose alpha value between 0 and 1. And all I'm doing is that I'm not giving one value. All I'm saying is that test all of these values and find the best values that you can find within those given alpha values. And what are these? These are the alpha values from 0.1 to 0.2, and increment is 0.05. And out of all that, you can get, for the grid, alpha and lambda both values are changing. For each of these grid, you are getting all of these ROC values, right? And of course, reading the numbers are not going to be easy. So you can get a really nice diagnostic plot, and you can see 0.01 and 0.01. So alpha is going to be your mixing parameter, and regularization parameter is lambda. So you can see all of these values that are here. So, but you do not even have to look at the graph to figure out which is your best tuning parameter. At the end of this, it will automatically say the final values used in the model were alpha 0.01 and the lambda was 0.05. It will automatically give you the best tuning parameter that are available within all of the parameter grid that you have given. And this is true for all of the machine learning methods that you use within the caret function. You can use as much grid value as you want if you think that there are competing grid values that you can, or parameter list that could give you better estimates. And that this would automatically find the best value based on the ROC or whatever metric that you use. Okay, so far we have talked about regularized machine learning methods, lasso, regression, elastic net, right? The purpose of those is bringing stability in your model or reducing collinearity issues. There are other type of machine learning models which are known as decision trees. And decision trees generally known as the classification and regression trees, because they can handle not only the classification or the categorical or binary outcome, but also the continuous outcomes. And these are very flexible. That means that in a, say for example, in a logistic regression, if you wanted to have a interaction between, say for example, gender and income, you would go ahead and put that gender multiplied by income in your model, right? Without you putting that interaction in your model, the model will never be able to figure out that that interaction you are interested about or that interaction is useful. Decision tree is something else. You do not have to put that interaction. You just specify the main effect terms. It will automatically determine the functional form. Because this is sort of a non-parametric scenario that we are going on. There is no particular beta coefficient that you get out of these decision trees. All the decision trees is doing is that this is following a very specific algorithm to figure out what is the best possible algorithm, or sorry, the functional form that you need to predict your outcome. You do not have to specify the interaction term. You do not have to specify square term. Even sometimes it is possible that you might have to square root some particular variable to get the better prediction. You do not have to specify anything. All you specify is the main effect term, age, sex, income, and all of these variables that you have with the specific. So that is the biggest strength of this decision tree, because in a real world scenario, think about your project that you are doing maybe for your graduate studies, that you are dealing with a data analysis. You are given a data. You do not know which variable should be interacted, which variable should be having a polynomial term or other functional form. There could be other complex terms, right? And sometimes there could be even three-way interaction terms and all that. You do not know, as a realistic analyst, you do not know. But when you are using this decision tree is actually telling you like which functional form is going to be useful for you. So in terms of decision tree, of course, there is a package called R within R to kind of figure out the relationship between the outcome and the covariate. Say, for example, in this example, what I am going to do is I'm going to use a covariate called the Duke activity status index, or the DAS index that I'm going to use. And I'm trying to use this DAS index to predict death. What this decision tree is going to do is it is going to split up the values. So you should know that DAS index is a continuous variable, and this has some measurements between 11 to 33. What it will do, it will say that if index value, DAS index value is greater than or equal to this, then go to yes, that there will be a death. And if the index value is less than that, then you come to the second decision. And the decision then is whether this is greater than 29, then you have death. If you have less than that, then there is no death, right? So this is the way it tries to determine. And you can imagine this is doing it for one variable only. And for many variables, it can make a huge decision tree, right? So you can also try to use that decision tree and try to get the predictions. One thing to note is that this decision tree that I'm using, what is the outcome? Death, right? So what is the measure of prediction I'm going to use? ROC, right? So for the ROC, all we need to do is just supply the fitted values here. And you can see in here, I'm specifying the probability values. I'm also specifying the second column, because since this is a classification problem, it will give the prediction of both death and no death. So there will be two columns, just like at the beginning I was saying. So you need to specify which column you need to specify. So you need to be a bit more careful when you are dealing with the classification problem. Once you have done that, you can get the ROC plot like this, and you can see the ROC is 0.59, right? Just by using one example, one covariate, sorry. And you can have your CART model or the decision tree as large as the previous models as well, using all of the covariates. And then you could still use ROC and get the AUC values. And the AUC values that you are getting using all of these is again this. So you see, just using the DAS index and all variables, you are getting very similar AUC values, right? So there comes the idea of variable importance, like which variable is important in your model. So one of the nice things about this CART model is that it will tell you which variable is more important than the other variables, right? So if you are just using that fit and the variable importance, you will see the DAS index is the most important variable. And then the cancer and age. So it will actually give you the rank of which variables are important. This is very different from the general regression that you have seen in your statistics classes. Okay. And of course, one of the biggest challenge of this CART method is that this method is very unstable. So all of these things that you are seeing, if you run the same model once again, you might get a different result, right? And that is very disappointing because this model has so many potential, but it's such an unstable method that, like, if you in your own computer, if you are not setting seed or changing your seed, you will get very different results every time you run it, right? So of course, one of the ways to bring stability would be to use the cross-validation to see what is the model. But the problem with that is that every time you are doing cross-validation in each of these folds, the trees are going to be different, right? And then you are sort of getting a lump sum result out of all that. That is very hard to interpret, but in terms of your prediction ability, that can increase slightly. So as you can see in here, based on different parameter values, you are getting some ROC estimates that goes from 53 to 63%. So that can give you some idea of what is going on in this. Okay, so in this particular slide, what I have talked about is decision tree models are very different than the general regression method that we use. That has some clear advantages, such as you do not have to specify the functional form, interaction polynomial or anything like that. But it comes at a price. It is very unstable, right? And when you do this, even when you are doing the cross validation, you can see there are some variability even within the same cross validation that you have done. Okay. One way to address that, as I have mentioned in my pre-reading slides and the video, is that you can do ensemble method. What that means is that you can do boosting, which is an extension to this CART method. And the idea is very simple. You have a data set of 5,700, right? You can repeatedly sample from this to create another data set of 5,700. And you can also take the repeated sampling to create other samples, right? And that is something we call bootstrap, where we are basically repeatedly sampling to get another 5,700 subjects in a data set. Another 57 subjects in a data set just by repeatedly sampling the original data. And in each of these data sets, for example, you do it for 1,000 times. In each of these data sets, you do this the CART thing. And then you get some estimates, and then you average out all of these estimates at the end. That is what we call as, bagging method. And this is the general idea that you just take independent samples, B times B could be 1,000, and then you apply 13 each of them, and then you just get the average of the prediction, and you get the ROC maybe. And then you will see the variance will be highly decreased compared to a regular CART method. But you do not have to do it manually. All you have to do is, in the method, in terms of our part, you have to specify bag, and that will do everything for you automatically. And that has all of these bells and whistles that comes with the CART. You do not have to specify any interaction terms or polynomial or anything, but it is on top of that stable, which was the #1 problem for the CART method, right? So you can do all of that using the bagging method. And boosting is slightly different approach, where you are again doing the repeated sampling, but you are learning from something from the previous sample. So the samples are not totally independent. And if you do that, you can, the only thing that you need to change, instead of that, you just mention GBM or the generalized boosting method, and that will give you some estimate. Okay, similar to the CART method, bagging and boosting, both method will give you the variable importances, right? And obviously variable importance can be measured in many different ways. And it is in the bagging method, it is very easy because you are doing it like 1,000 times, and you can just simply count how many times one variable was there, right? And that will give you a slightly different estimate. See, now age is the #1 value that is important. Aperture index, then the DAS index and all that. And you can just rank them and try to find out what is the most important, say 10 variables out of your model.